Welcome back. We'll finish our discussion of triangles by discussing right triangles, which have special properties that can be tested for on the CLEP exam. So recall, a right triangle is a triangle with one right angle. And of course, a right angle is an angle that is 90 degrees. It's a worthwhile question to ask, why can a triangle not have more than one right angle? Well, that would mean that those two angles had 180 degrees between them. And of course, the total sum of the angles is 180 degrees. So this would make the other angle 0, which leaves us not with the triangle, but a flat line. So the key result you have to keep in mind for right triangles is what's called the Pythagorean theorem. So right triangles enjoy a special property called the Pythagorean theorem, which, as the name suggests, was known even to the ancient Greeks. So what does the Pythagorean theorem say? Well, it's classically phrased as follows. Okay, so here I've drawn a right triangle. We call this length here C, this length here A, and this length B. So this side is called the hypotenuse, another nice Greek word. And it's special because it's the leg that is opposite to the right angle here. It's the longest leg of the triangle, of the right triangle. And these two, A and B, are both called legs. So what does the Pythagorean theorem say? It says the hypotenuse squared is equal to the sum of the legs squared. Or mathematically, A squared plus B squared is equal to C squared. How could this be tested? Well, it could be tested by saying, ask you to compute one of the missing legs of a triangle when the other legs are given to you. This is only easily done with a right triangle because we have this amazing Pythagorean theorem. So let's look at some examples where we're asked to solve for some missing legs. So first, we'll look at the following triangle. So it's a right triangle. This side is 5, this is 8, and this side x is unknown. And we want to solve for x. If we use the Pythagorean theorem, which I'll say PT, this tells us that x squared plus 5 squared is equal to 8 squared. And now we just have to solve for x. So x squared plus 25 is equal to 64, which tells us that x squared is equal to 64 minus 25, so that x squared is equal to 39. And now we have to take the square root of both sides. So x is equal to the square root of 39. So as a general remark, when one goes from here to here, you would expect to get a plus or minus for the square root. But because we're talking about side lengths, which are known to be positive, not negative, one just eschews the negative sign and only returns the positive square root here. This is just because it doesn't really make sense to talk about a negative side length. So we just write square root 39. Pretty straightforward, I think. Let's look at another example. Suppose we wish to solve here for x. Again, because I have a right triangle indicated by this square block, I know that x squared plus 4 squared equals 5 squared, so that x squared equals 25 minus 16, which is 9, and then taking the square root, I get 3. So in this case, I get a triangle with side lengths 3, 4, 5. In module 7, we'll discuss the idea of an integer, but suffice it to say it's essentially a number without a decimal expansion. So here we have side lengths of a right triangle where all of them are integers. This is very special. This is what's called a Pythagorean triple. Rather, the triple 3, 4, 5 is a Pythagorean triple. Here, square root of 39 is not an integer. It's some infinitely long decimal expansion. Let's look at another application of these triangles. Suppose we wish to compute the area of a triangle. Let's look at one. So I know this is 3, and I know this is 8, and I want the area. How can I do this? I'm not given the height of the triangle. I know that A is equal to 1/2 base times height, but the height's not given here. The base is given as 3, but the height is this unknown side. So I need to be able to solve for the height, and thankfully I can do that using the Pythagorean theorem. I know that 3 squared plus h squared is equal to 8 squared. So this tells me h squared is 64 minus 9, which is 55. So that h is the square root of 55. So that was step 1, to find this missing side length using the Pythagorean theorem. And now I can plug that into the area formula and say that area is equal to 1/2 base times height, which in this case is simply 1/2 times 3 times square root of 55. So maybe something like 3/2 square root 55. Again, square root of 55 is not an integer, so we'll just leave it as a square root. Let's do one more example like this. Let's say this is 7. And the base is 5 here. We have a right triangle. So again, to find the area, I'll use the formula 1/2 base times height, but the height is currently unknown. So I'll use Pythagorean theorem to solve for it. 5 squared plus h squared equals 7 squared, so that h squared is equal to 49 minus 25, which is 24. So that h is equal to the square root of 24. And now I can plug this in up here. The base is 5, and I get square root 24 here. So 5/2 times the square root of 24. This could perhaps be simplified further, noting that this can be written as 5/2 times square root of 4 times square root of 6. So 5 square roots of 6, though that's not necessary. The basic idea of right triangles for us is to identify them and to use the Pythagorean theorem to get some extra tools to work with certain types of problems related to finding side lengths. But we can go beyond side lengths. We can also do area problems in this way.